Good afternoon, everyone. I am Mr. Ish. Thank you for joining me for this video. Now we will begin our topic of derivatives. You might know that calculus has two main branches. You have the differential calculus, which deals primarily with derivatives. Then there's the other branch, the integral calculus, which deals with the integrals. When we're talking about derivatives, you're probably familiar with the notation. We're looking at something which looks of this form. If you have a certain function f of x and you have to determine the derivative of this function with respect to x, this is basically what you're looking at, how you're determining the derivative of a given function so that you can come up with a certain value. And as I've mentioned before in the rate of change videos, this value over here is going to represent your instantaneous rate of change. And you can contrast this to what you know about the average rate of change. Remember, the average rate of change was derived from the slope of a secant line, whereas the instantaneous rate of change was derived and it represented the slope of the tangent line. The average rate of change was noted to be perhaps less applicable or less important than instantaneous rate of change, because for whatever model or function that you are analyzing or that you were to analyze, the instantaneous rate of change would provide you the information of what was occurring with that model at a given point of time. So the instantaneous rate of change has important applications to it. And that's the whole process and the whole point of even studying differential calculus, which deals with derivatives. As a very quick starter, you remember the video where I presented that the derivative of a given function, and that function could have been an f of x as limit, you might remember this, limit h approach 0. The formula we used over here was f of x plus h minus f of x, meaning the change in y divided by the change in x values for a given function. If supposedly you had a given function over here and this represented your x value over here, and you went 8 units ahead and this represented here your x plus h value over here, the coordinate, and you know, looking at this point over here, we were looking at x comma f of x. These were the coordinate pairs for this value, and this value over here represented, this dot over here was x plus h comma f of x plus h. The f of x plus h represented the input as you put it into your function, that was your output. So the f of x plus h represents the input of f of x plus h, giving you the rise of that output, which is represented in terms of the y value over there. y2, x2, y1, x1, and you could have done the slope y2 minus y1 divided by x2 minus x1, which gives you this formula over here, f of x plus h minus f of x divided by h. I've kind of run into that formula over here, and I have also presented you that in another video. The derivative process, and the purpose of learning derivatives is to simplify all of this. I want to start by showing you an example with application of this, then we'll go directly into the application of derivatives. And the whole process of learning derivatives is not hard at all. You just have to learn the various different formula or the formulae, or you can even call them templates if you want, the various templates for the various types of functions you'll see in calculus. Each different type of function or style of function has its own template that you have to follow. We're going to look at the templates in this video for polynomials, right? Polynomial templates are the easiest to see. If supposedly you had a function which looked like something like 2x squared minus 1, and someone said you have to find the derivative of this. The derivative of this with respect to x, you have to find that for this specific function. You know, I'm telling you, we're using the previous formula, the f of x plus h minus f of x over h, and then you would proceed with that in this following manner. Limit as h approaches 0, your function underwent the following process. You would do this, x plus h whole square minus 1 minus the f of x value, f of x expression, which would be just 2x squared minus 1, and you would divide this by h. You would open up all of this. You'd have 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared plus 1. You're opening up the parentheses over here. Let's make this a little neat over here. This over here became a 4xh, and you have all of this divided by h. And then you could also cancel out terms over here, opposite terms, they cancel out, leaving you on the top with this part right here, 4xh plus 2h squared over h. If you were to isolate h from over here, you would get 4x plus 2h over h, and you would cancel out the h's over here, and you're still looking at this assumption over here as h approaches 0. This value over here, 4x plus h, would actually approach 0, and you would be left with the following answer. Your derivative of this function 2x squared minus 1 would be just a 4x. This value over here which you see, this is what you would get over here. Using this process, I call this a more elaborate process. This actually is a function process, a function related process for determining derivatives. But this process over here, f of x plus h minus f of x divided by h, is easy for polynomials. But as you start doing trigonometric functions and exponential functions and logarithmic functions, this process can become very difficult, which is why you need to spend the time in learning the derivatives. If I were to do the same question over here for this function over here to find the derivative, which gives you the instantaneous rate of change, I would have done only this, the derivative of this function 2x squared minus 1, and I would just look at this right here. I would look at it and I will know instantaneously my answer is a 4x. A 5-second process versus a more elaborate process. So this process is here. The substance of this video, the polynomial derivatives, is what we're going to look at. And I'm going to show you the template and the techniques for doing this process for polynomials. So we start with the template. If your function is a x b, where a represents the coefficient, b represents the coefficient, you know what polynomials are. Polynomials can be a single term, it can be a double term, a binomial, it can be 3 terms, a trinomial. You can have a certain given number of terms. If they are arranged in an order such that you go from the high exponent down to the smallest exponent in terms of the degree or the order of those exponents, that right there is a polynomial. So our polynomial here is f of x is equal to axb, and we are learning now how to determine the derivatives of the polynomials using the easy technique. Let's just call this the easy technique because for all instances and purposes it is actually an easy technique. This function here has a coefficient a and it has an exponent. So what's a template or what's a formula you would use to determine that derivative for any polynomial? And it would be this. Look what I'm going to do. The b came out as a coefficient and multiplied with whatever coefficient you already had. The coefficient here was a, so b multiplied by a. Whatever the exponent b was, it was reduced by 1 during that process. So this right here represents your procedure. A very easy example to demonstrate. If this is my number here, 2x squared, you're going to bring 2 over here and it'll multiply with your existing coefficient. Your existing coefficient here is a 2. You'll get 2 multiplied by 2. Here's my b term, here's my a term. 2 multiplies with that 2, and whatever exponent you had was decreased by 1. Look what you actually get. You get 4x to the 1, or you can just say 4x because x to the 1 is the same thing as 4x. So this right here, this over here, and this stuff right here in between the 2 arrows represents your scheme or your template on how you do this process. Now look exactly at the very first example I showed you in the previous image, or this previous still to this was, remember we were determining the derivative during the long process of, I believe it's 2x squared minus 1, and I did it in 5 seconds. How did I do it? Well, one was a constant, it had no derivative, and we'll be talking about why constants have no derivatives. I did a quick multiplying here, 2 by 2, and I had a 4, and the exponent was reduced by 1, and I had a 4x. If I remember correctly, this was the example I presented. I hope it was. But anyhow, you're seeing over here the procedure, the process of this template, the scheme as you want to call it. A very quick another example. If someone told you to find the derivative of 3x to the power of 5, you know very quickly to follow this procedure right over here. This 5 will multiply over here with your existing coefficient, and your 5 will be reduced by 1. So 5 times 3 is a 15, and the exponent will be reduced by 1. You'll have x to the power of 4. So 15x to the 4 will be your derivative of this item. This derivative, if you were to plug in an x value from a coordinate pair for whatever function you're looking at for an xy coordinate which happens to land on that curve, if you were to plug in this x value over here and you plug it in and you solve this out, you would get your instantaneous rate of change at that specific point. which will represent the slope of the tangent line at that specific point. So the template and the scheme has been laid out to you for polynomials. It's basically this: ba times x to the power of b minus 1. I need to just show you some quick rules which will accompany this. Those rules are not really formal rules by any means. They're just ways and techniques that you can use to simplify the whole process. Or when you see a question of a given type, what you should be doing in your head before you tackle that question. So that's what I'm going to talk about, various conditions that you want to do first. So when you're doing derivatives of polynomials, these are the conditions you want to see before you actually determine the derivative, because these are the conditions which will simplify your whole process. At any time you have in your polynomial an expression which has an exponent but in the denominator, just bring it up and bring in a negative exponent. Rather than doing a derivative of a term which is in a fraction, bring it up and look at this as your term for doing your template or the scheme as I was talking about. When I show you examples, you know exactly what I mean. So prefer this format over this format. Anytime you have a constant, and let's say c as your constant, like if supposedly someone told you to do the derivative of 5. Now that's a constant, right? You will want to look at your constants in this form as if you're looking at a constant which here represents a numeral, a number, and it is attached to something to the power x to the something to the power of 0, and anytime you see a constant, the derivative of that will always be 0. And the reason why it'll be a 0, because if supposedly you represent 5 as x to the power of 0, this numeral to the times x to the power of 0, because anything to the power of 0 is always equal to 1. 5 times 1 is a 5. And then you follow the template I told you. You multiply the 0 with the 5, and the exponent is reduced by 1. So technically you've zeroed it out, haven't you, right? 0 times 5 is 0. Everything which happens with x is meaningless now, which is why for all constants, if you view them in this format, the derivative of any constant will always be a 0. So if you see a constant in your large polynomial, don't waste time trying to calculate its derivative. Put a 0 in its place and let that 0 affect that question as it normally would. Anytime you see a radical, let's not talk only about square roots, let's talk about n roots. Anytime you see a radical, try not to view your radical in this format, rather convert it into this format. X to the power, and here whatever the exponent might be, let's call it m. View your radical in this form right here. And you remember this from the law of exponents and radicals. A to the power of m over n is the same thing as saying n root a to the power of m. The only reason why I'm telling you to view this or prefer this appearance over this appearance, because technically doing the derivative scheme or the template or the formula of this format is much easier than looking at it in this way. Just like looking at it in this form is much easier than that form, this form is much easier or is visually more appealing and easier to calculate than in this form. Anytime you have multiple aspects in your polynomials, for instance, let a represent part of your polynomial and you have a plus or a minus b and then a plus or minus c. A could have been a proper, and here a, b and c, I'm not talking about constants, a, b and c could represent proper monomial terms. Like a could have been like a 2x squared, b could have been like a 5x, and c could have been a root x. I'm talking about these in just hypothetical sense. Anytime you see something which looks like this and you have to determine the derivative of this expression, split it up. You would split it up as this: individually, you'll just separate them out. And you can, like, you would distribute that polynomial derivative in this form. You will distribute it. Then individually for these terms you can do their derivatives, and then you can come up with your normal expression. And you don't have to do this by any means. It's just something you may opt to do because it's easy that way, but you don't have to do it. And I'm not talking about multiplying and dividing. When you're multiplying terms and dividing them, there's a specific additional rule or template you have to follow, but that's not the subject of this video. I'm going to be showing you examples here of polynomial derivatives which will only involve a positive or a minus, like in addition or subtraction. We're not going to bring multiplying and dividing yet. That might be the subject of another video, but keep all of these in mind. If you see something like this, convert it into this. A constant derivative is always equal to 0. A radical should be converted into fractional exponential form, and you can separate you can just separate an expression into individual terms with their individual derivatives. let's put all of this into examples so we can clarify all of it. Alright, so I have created room over here. I removed the title, but I've put this over here. This right here is our template or scheme or the formula for determining a polynomial derivative. Our question is this: if someone told you to find the derivative, and remember the whole process for doing derivatives is to contrast it to the process you've learned before, which looks something like this, which is more elaborate and more difficult. You're now learning the easier way. Alright, these both will give you the same things. Anyhow, your question is if someone told you to find the derivative of this polynomial, x cubed minus 4x plus 1. Now think back to what I told you in the previous image, that you have something like this. You can separate out into its terms. You don't have to, but you can. If you chose to separate it out, you would do it like this: d over dx half x cubed minus d over dx. The derivative with respect to x, you can say it like that, plus derivative with respect to x of 1. Now look over here, I've separated everything. I didn't do anything with any of the signs. You can even take the other fancy step of taking all of these coefficients and bringing them over here. And this is what I'm talking about. You can do 1 over 2 d over dx, x cubed minus 4. You see, I brought these coefficients before because the coefficients are not going to do much, and you wouldn't do anything over here because this right here is a constant plus d over dx 1. This is just a way for you to learn how to separate things out, but you can separate the coefficients from their variables. You don't have to do this, because if supposedly you didn't choose to do this, you would not be wrong at all. When the derivative polynomials get more complicated, then it's a time for you to do that, but right now it isn't. Anyhow, for each of these items now, let's look at the scheme. The exponent, which is your b term, will multiply with the coefficient. 3 will multiply with 1 over 2, you'll get 3 over 2, but the exponent 3 will be reduced by 1, and you'll get x squared. And this 1 over here, because anytime you don't see an exponent, it's always assumed to be a 1. 1 will multiply with the 4, right? And your exponent for that variable will be reduced by 1. You'll get 1 minus 1, you'll get to the power of 0. Plus, now look, remember the condition I told you before, or you can call the word condition a rule. Anytime you see an a constant, it's always equal to 0, because the variable it was attached to was x to the power of 0. You'll multiply 0 with the 1 and you'll zero everything out. So constant derivatives are always equal to 0. You can actually entirely eliminate them if you want and not even consider them any further, because this thing right here is zeroed out. Now look at what you get over here as your final answer. It's nothing more different than you writing it in a better way, 4, because x to the power of 0 is a 1, 4 times 1 is a 4. So this right here represents the derivative of this function. This would have been f of x is equal to x cubed over 2 minus 4x plus 1, and someone had told you to find the derivative of this, because somewhere on this, this point lies on this curve 0, 1, and you have to find the slope of the tangent line or the equation of the tangent line at 0, 1. Well, you would first proceed through this process over here, and once you get this 3 over 2x squared minus 4, you see this x value over here, you would plug this over here in place of x. And when you would get as your slope of this tangent line would be equal to minus 4. Because when you put 0 here in place of x, right, you get 3 over 2 times 0 zeros out, you get left with only a minus 4. So the slope of the tangent line to this function at 0, 1 would be a minus 4. Then using minus 4 in these 2 points, you could actually come up with the equation of that tangent line. But we don't have to get into all of that. Right now we're only talking about calculating derivatives. The whole purpose of calculating derivatives is for whatever model you're studying or analysis you have to do to determine the instantaneous rate of change or the slope of the tangent line at a specific point you might know. But you need to have the derivative obtained first before you can do these next 2 steps. Let's look at some more examples. Now for this question, you have a function which is represented here. I'm not using the functions in the f of x format, though they all are. This is f of x is equal to 2 over x squared minus root x. But anyhow, for that function, you have to determine the derivative, because somewhere down the road, you have to determine the slope of the tangent line or the equation of the tangent line at a given point, which will be on this curve. Think back to some of the hints I told you earlier, that when you see those specific conditions, you want to rewrite your expressions in that form. Well, here you have a variable with an exponent in the denominator, and here you have a radical, so rewrite it out in that form which I talked about, and the rewritten form will be 2x to the power of minus 2. See, x comes up with a minus 2 exponent, because the minus here simply implies you have a reciprocal. Alright, the reciprocal. You can bring up an exponent and put a minus 2, and you know this can be written as 1 over 2, because the square root is a 1 or 2 exponent. And now using this more friendlier format, you can exactly carry this part out. You can. Minus 2 will multiply with 2 to give you a minus 4, but the minus 2 will be reduced by 1, you'll get a minus 3, right? Minus 2 minus 1 is a minus 3. Half will multiply with the coefficient you see here. If you don't see a coefficient here, it's always assumed to be a 1. It'll just be half. Half times that 1 is a half. And this exponent will be reduced by 1 to give you a minus 1 or 2. Now this over here can represent a final answer, but it's not the best final answer because you got negative exponents. Get rid of the negative exponents, rewrite everything without the negative exponents. Well, now you're going to shoot the x back down into the denominator, but with a positive exponent, minus 4 over x cubed, which is fine. And then you'll have minus 1 over 2. X is going to come down, but as a root x. Think about it, it would have been 1 over 2x to the power of 1 over 2, but you're converting that 1 over 2 back into its original square root. This minus 1 over 2 meant that your variable was in the denominator with a root. So not a hard question. This right here represents the derivative. Now imagine for the same question if you were trying to do it into this format, in this way, f of x plus h minus f of x over h, and you had to plug in this in place over here and in place over here, and then start analyzing it and simplifying it and then running the assumption h approaches 0, and then down the road somewhere you would get your final answer, and there might be some rationalizing involved, but this procedure here is so much easy. It's so easy. This is why derivatives are just real good. This is the whole branch of differential calculus. Anyhow, we're sticking our conversation today to the topic of polynomial derivatives. And here, as you can see, I've only talked about adding and subtracting. I haven't even talked about multiplying and dividing, because that will be a whole different addition to what you're seeing over here. Let's look at more examples. So in this question, we're tasked with determination of the derivative of this function with respect to x, and what can that derivative be. Again, everything is here in a polynomial format. Either you have things adding or you have things subtracting, but there's no multiplying or dividing going on, because that's a specific nuance which will come into play for that, a specific set of rules. But let's stick to adding and subtracting only. Again, I would rewrite this in a more friendlier format. The friendlier format would be 7x to the power of minus 1, bring it up. Minus 2x to the power of minus 2, bring it up. And this is a cube root of x. I'll write this in a fractional exponential form. See, I brought this as a fractional exponent. Nothing wrong with that. Now, in this friendlier format, do your derivative scheme or the template or whatever you want to call it. Minus 1 will multiply with this 7, and you will get what? You'll get a minus 7. But at this minus 1 will be reduced here by 1, you'll get a minus 2. But look, minus 2 will multiply with this 2 to give you a minus 4. Now you'll see a sign will change over here, but this exponent of minus 2 will be reduced by 1 to give you a minus 3. Now look over here. 1 over 3 will multiply with the x, the coefficient you see over here of this x, which is a 1. You'll get 1 over 3, and the 1 over 3 will be reduced by 1 to give you a minus 2 over 3. See, 1 over 3 minus 1 is a minus 2 over 3. So you're seeing as we're carrying it on, it's just algebra playing over here. The derivative part was just this rule you have to follow, the scheme. Now we finalize our answer by writing things in a more proper format. The minus 7 stays on the top, and x goes back down to the positive exponent. This minus, and this minus become a positive, and we have a 4, but x goes back down with the positive exponent, x cubed. We have to bring everything down over here, because keeping your answer in negative exponents is not a good thing, even though you're using them for the procedures, but the final answer should have positive exponents. Bring everything down. 3x to the power of 2 or 3. See, x to the power of 2 or 3. But you can write this in a better way. 3 cube root x squared. 3 times cube root of x squared, and this right here represents your derivative of this function. Had you access to a given point x comma y on this function curve, this x would be valued, the numerical value would be plugged here in places of x, and it would give you a slope of the slope of the tangent line, which would be your instantaneous rate of change. It would tell you exactly what's happening at that specific point, at that specific point on the curve, how your function is behaving at that specific point. And then from that specific point, and using these two values, you could get the equation of the tangent line. We're not talking about secants, we're talking about tangent lines. I want to show some more examples, and we'll wrap this up. Okay, let's look at this function over here, and we have to determine the derivative, because the derivative will represent some factor. If when we plug the x numerical value into that factor, we'll determine our instantaneous rate of change, which then can be applied towards the tangent line. And this represents our function over here. The only reason why I'm giving you these polynomial functions with multiple terms is because I can show you multiple applications of the derivative for each of these terms, so it actually increases the amount of examples I'm showing you versus just putting only a single term for each of the various questions. Here we end up having multiple terms, we see multiple applications of the polynomial derivative formula. Again, rewrite everything in a more friendlier format where and when you can. X stays as an x, 4 root x becomes 4x to the power 1 or 2. It's easier to see that than a radical sign. You gotta bring this radical up as x to the power minus 1 or 2. The 2 stays down because it's still like a coefficient. 1 or 2 root x is x to the power minus 1 or 2 divided by 2. And this thing stays as is, and 7 stays as is. And you're still having to determine 1, 2, 3, 4, 5 different term derivatives. Well, x over here is the same thing as x to the power of 1. So let's not do the derivative application. 1 multiplied with the coefficient of x, which is a 1, you get a 1. But x over here happens to have 1 minus 1 applied to it, becomes to the power of 0. See, 1x to the power of 0. It zeroes out over here, but that's fine. What happens, we'll see. Look over here, 1 over 2 multiplies with 4, you get 4 times 1 over 2, which is a 2. And the exponent will reduce by 1 to a minus 1 over 2. Minus 1 over 2 will hit with this 1 over 2 to give you a minus 1 over 4. And in itself, it will be reduced by 1 to give you a minus 3 over 2. 1 over 2, minus 1 over 2, or minus 1 is a minus 3 over 2. 2 over 3 will multiply with this 2 to give you a 4 over 3. And this 2 over 3 will be reduced by 1. 2 over 3 minus 1 will give you a minus 1 over 3. And you know, for constants, derivatives are always 0. So never even waste time with that. Now let's come down over here. 1 times x to the power of 0 is just 1. Easy. Anytime you have a variable with only an exponent of 1, you'll basically, whatever the coefficient was, it could have been 2, 3, 4, 5, whatever, it'll come down and you'll have lost the variable. Let's look at this next one. You just have to rewrite this in a better way. 2x root 2 root x, because it was x to the power 1 or 2, and let's just convert it into a radical form. Minus times minus gives you that plus, and let's write this in a better way again. 4, you have x to the power of 3 or 2, which is really 4 square root of x cubed, because you have a denominator which serves as the index of that radical, and this numerator which serves as the exponent of your variable. Let's look over here. 4 over 3 x to the power of minus 1 over 3 is the same thing as saying cube root x, and then plus 0 is nothing. We don't even bring that up. But here represents your final derived value, or the derivative with respect to x for this function over here. But again, you saw the derivative polynomial technique, this formula right here, being applied all the way across in the various types or scenarios that you would see. And I hope it's proving to be beneficial for you. The main thing you need to remember over here is this. Anytime you have something which looks like ax to the power of b, the exponent multiplies with the coefficient and the exponent is reduced by 1. Not too hard. Let's look at this question. Again, a polynomial with multiple terms, so I have multiple opportunities to show you how this rule is applied. By now it should not be too hard. I would spend the time in rewriting all of this in a more friendlier way. This right here is already in a friendly way. 2x to the power minus 4. It was probably 2x, 2 divided by x to the 4. You bring the x up, it becomes x to the minus 4 plus 3x to the minus 3. See, I'm rewriting all of this, and I should be putting a derivative over here because we have yet to apply the derivative. And this term will come up as 1x to the power of minus 1 over 4. 1 over here is redundant, but we can still keep it. See, x to the power minus 1 over 4 plus derivative of 2. We have to actually do the derivative step, so let's do the derivative step. 5 multiplies with 3. Remember this. B multiplies with a, and the b is reduced by 1. 5 multiplies by 3, you get 15. 5 is reduced by 1, x to the 4. Let's do minus 4 times 2 is a minus 8. Minus will hit with this minus and make it a plus. So let's skip that one step. 8 x is reduced by 1, it becomes a minus 5. See, minus 4 minus 1 is a minus 5. Minus 3 multiplies with this 3 and you get a minus 9. And this minus 3 is reduced by 1, x to the minus 4. Let's look over here. Minus 1 over 4 multiplies with 1 to give you that minus 1 over 4 coefficient. And x is reduced by this x exponent, minus 1 over 4 is reduced by 1. You get a minus 5 over 4. The derivative of any constant is always 0. Never waste your time with that. Let's just rewrite our final answer in a more approved format with no negative exponents. 8 over x to the power of 5 minus 9 over x to the power of 4 minus 1 over 4x to the, well, let's make space over here because I have to bring a radical over here. It'll be 4 fourth root x to the power of 5. See, this denominator serves as your index of your radical, the numerator serves as the exponent of your radical expression over here, and plus 0. But here represents our good answer and we're done. I don't see I'm making any silly mistakes over here, but I feel like we're doing everything well over here. I should present you one more question and we should wrap this polynomial video derivative with that. And I'll keep it a comprehensive type of example. So as our last comprehensive example, I'm presenting you again yet another polynomial. No monomial, it's like multiple terms in here. I want to spend the time over here as my first step to rewrite this in a better, friendlier way. And you don't have to even do it, you can go directly to your procedure. I'm doing it only for the sake of the video and to exemplify the fact that it's sometimes better to look at it in an easier way because you're less likely to make a mistake that way. X squared comes up as 10x to the power of minus 2 plus 2x minus this x comes up as to the power of minus 1 over 2 because it's a negative exponent over here, which means it was a reciprocal. You're bringing it down. Let's make this look more like a 2 and less like a mess. And then plus 3. Now you actually have to do the derivative of each step. The exponent will multiply with each of the coefficients. 3 times 4 will give you a 12 and each of the exponents will be reduced by 1. You'll have x to the power of 2. Minus 2 will multiply with this 10 to give you a minus 20, but you have already a minus here, so it becomes a plus 20. X exponent is reduced by 1, it becomes a minus 3. Now look over here, this is x to the power of 1. 1 will multiply with 2 to give you 2, but x will be reduced by 1, you'll get x to the power of 0. That's what I was saying previously. Anytime you have a variable with an exponent of 1, you might as well eliminate that variable and just keep the constant because you'll be left with a constant in the end anyways. But we'll see that happen anyways. This minus 1 over 2 will multiply with the 1 which you see over here, an imaginary 1. Minus half with that minus sign will give you a plus half. And the variable exponent will be reduced by 1, you'll get a minus 3 over 2. And for any constant, the derivative is always a 0. The very last step involves rewriting this in a more acceptable format. You'll have 12x squared plus 20 over x cubed plus 2 plus 1 over 2 root x cubed. This is your index of your radical. This right here is your exponent aspect of your variable which sits within that radical, and then a plus 0. So here is your final answer. Right here is your final answer. If supposedly you had a given point x comma y, a specific point, if you had graphed this out and it lied onto that and it existed onto that curve, and someone told you to find the slope of the tangent line at that specific point, you would take this x value, whatever numerical value it was, you would plug it in all of these x's and you would come up with a specific numerical answer. It could be a decimal answer, a fractional answer, or a whole number, and that right there would give you your slope. It would give you your slope of your tangent line, which would represent the instantaneous rate of change, that what exactly is happening at that specific point. Then in conjunction with this slope and these 2 points, you could create a equation of the tangent line just using the formula y equals mx plus b. That's where you would actually apply this whole process. Using this slope and these 2 points you were given in your question, you would determine the equation of tangent line. So that equation of your tangent line would be very good in the sense that it would be in this form, and that tangent line would graze your entire function at that one specific point. It would barely touch it, but it would touch it at this specific point, and you would know the slope, and you would have the equation, and the slope would give you your instantaneous rate of change, which is the whole procedure why you're even learning derivatives. But today we only talked about derivatives of polynomials, and you saw how it contrasted very easily, but in a very sharp contrast to the other procedure of f of x plus h minus f of x divided by h. This procedure is just so much more easy, and it's so much more easier by using the table of approximations that I talked about in that video, or in the three videos actually, about the rates of change. But this is a procedure to know. The derivative procedure is an excellent technique. I would recommend all of you to stay tuned to my videos, because I'm going to be talking about derivatives of the various types of functions that you'll see. Not just polynomials, but the various types of functions. We'll be looking at the derivatives of all of those. And each of those procedures will have a specific formula for you to learn. You don't have to memorize these formulas because they're normally given to you in textbooks. But if you do these enough, you'll actually end up memorizing them anyways. But keep in mind the various nuances I presented over here, and the ways of writing these out in a more friendly format, and how you express your answer at the very end. Again, remember your coefficient here, a, is multiplied with your exponent, so you get a BA. But the exponent in the procedure is reduced by 1. That right there is a representation of the derivative of a polynomial, and we've only talked about adding and subtracting polynomials. We haven't talked about multiplying them. You'll have an extra little step or two involved with that, but that'll be subject for another video. I hope you enjoyed this video. Please like, subscribe, and share. Thank you for watching. Bye.